All right, thanks for coming. This is the second part of Lecture 0 for the class Real-Time Digital Signal Processing Laboratory at the University of Texas at Austin. I'm Professor Brian Evans, and glad you could be with us. So we had lecture on a couple days ago. Any questions from Monday's lecture? Okay, so just to repeat one question that happened earlier before we started taping. So you'll need to use MATLAB somehow during the class for homework and some of the lab assignments. In lab, MATLAB will be available on the PCs. In the laboratory, you can also use for homework MATLAB on your laptop, either through Student Edition or through logging into one of our servers. Or you can buy the full version of MATLAB, which is way too expensive. It's thousands of dollars. Student version's $99. Or you can use LabVIEW MathScript. Those are different options for using MATLAB in the class. Okay, so last time we went through most of the first two bullets here. We went through instructional staff and introduction to real-time digital signal processing, and we almost finished the course overview, so I'll pick it up there for today. So part of the overview, which we'll now skip slides to slide 14. And so this is now some of the obvious things. The course descriptor is still, if you didn't get it on Mondays, on the back table. So the grading is a pretty important question, where the point's going to be. There are two midterms, and I'll expand on each of these in slides. Homework, there are 8 of them, assigned not every week, but I give you a week notice before one is due. Pre-lab quizzes, which will not begin until Lab 2, so you don't have to worry about it next week, but starting January 27th, you will have one for Lab 2. These are multiple choice questions. We'll talk about that later. Lab reports, there are 7 labs. Now, it's an interesting thing at the University of Texas is the issue of an excused absence. So I don't know if you're familiar with the policies, we probably are by now. What's the only reason the University of Texas allows for an excused absence? And there's only one. Religious holiday, that's right. So if you have a mandatory observance of a religious holiday that precludes you from coming to class or participating in lab, let me know. All right, so you're supposed to let me know now if it's in the first 2 weeks, or at least 2 weeks notice if it's after that. And this is a pretty common occurrence. Totally cool. Other reasons are not recognized by the university. Now, this should kind of scratch your head. So the obvious ones are what? What should be probably recognized? Death should be recognized, but oddly it's not.
I was going to say childbirth.
Childbirth? There is medical leave for employment, and hospitalization is a more general question. So if there is hospitalization, I'll work with you. Let me know. We'll work around it. Not a problem. And it could be other reasons, flat tire, maybe that's not a good excuse. I don't know. There are lots of reasons to miss things. But hospitalization is a big one. Death in the family, this is a big one. Okay, so we'll work with you if you need to leave for bereavement or whatever. Absolutely, we'll work with you. Now, the good news is that there are, in 3 of the cases, you get to drop the lowest assignment. So this means that if there is something that comes up, then, okay, you get to drop one homework. You get to drop one of the pre-lab quizzes. There are 6 of them. You get to drop one of the lab reports. There are 7 of them. Okay, so this accounts for other things that can happen. Whether it's excused or not, it's not, whatever. Okay, so an excused absence, we'll have you make up the work, absolutely. For a thing that's not excused, then the good news is you get to drop one in each of these categories anyway. So if you miss it, or if you get to the end of the semester and decide Lab 7 is too much work given other things, you can skip Lab 7. Now, last semester, everyone did Lab 7, which is the first time it's ever happened. That was surprising. But it's guitar effects. It's a fun lab. Okay, so for each midterm, 21% of the grade, we're going to focus on design trade-offs and signal quality versus complexity. We talked a little bit about that last time. Lots of measures of signal quality. The basic measure was what from last time? What's the fundamental measure here? Yeah, signal-noise ratio is the one that we're going to... Right, so for signal quality, it's signal-to-noise ratio is our starting point, and we can expand that as the application warrants. So signal-to-noise ratio is the first stop, but it's usually not the end point in measuring signal quality. Okay. Complexity, we talked lots of different things there. Execution time, memory usage, memory input-output rates. Those are the ones we're going to focus on. You can go and close the door in the back, because that would be good. Thank you. And the midterm exams are going to be open book, open note, open computer. Just can't use a network for obvious reasons. So make sure it's your own work. This means that all the tools that you develop and use on your laptop, you can use during the test. So if you got your own MATLAB, you won't need to use MATLAB, but you might want to use MATLAB to check an answer. I will not ask you a question in MATLAB to write a MATLAB program or to tell me what a MATLAB program does, but it might be comfortable to have. You can download all the slides and the whole website, actually, if you want to, on your computer. I don't copyright anything for a reason. The videos may be copyrighted, it's a different issue, but in terms of the course materials, everything is uncopyrighted for a reason. So you can use it, and we can widely disseminate the information. Anyway, so the midterm exams, lots of them are in the course reader, dozens of them actually, and most have solutions. So it's all their last semester's exams are in there, for example. And they go back about 10 years for midterm 1. Midterm 2 goes back about 8 years, something like that. So the more recent midterms are more related to what we're going to cover. Test dates are on the course descriptor and the lecture schedule, which I'll show you the schedule in a second. The test dates are going to be, listen very carefully, Friday, March 7th. It's a very important day, not just in this class, but for other plans you may have for this semester. And why is that? It's the Friday before spring break. Okay, so plan accordingly. And the midterm 2 is the last day of lecture, May 2nd. So the exams will be during this time period in a different room. I'll get a big room, lots of tables, to write on, and lots of space to spread out, because you'll bring books and stuff with you. Okay, so lecture schedule, let's put that up. So here's the lecture schedule from the website. Again, we have a holiday for Dr. Martin Luther King on Monday. This is the table here, so we have lecture Monday, Wednesday, and Friday. So lectures are here. The lab, no lab this week, where we start on Tuesday. And the reading assignments are all here. And this is on the page 5 in your course reader as well. It's in many places. So all the reading assignments are here for the semester. And I'll put them on homework assignments as needed. But in the meantime, you don't have to wait for a homework assignment. Here's all the reading assignments for the semester. The labs also have some additional reading. So if you click on the pre-lab quiz link, that will take you to the lab webpage, and that will give you some additional reading out of the lab manual for that pre-lab quiz. Okay, so if you look at this, this is the schedule through spring break. And oh. All right, so I'll have to scroll in a second. So if you look at the topics in the lecture, a lot of this is going to be reviewing signals and systems, but as we review the material, for example, signals and systems here, and the very first couple of lecture periods for finite impulse response filters, we'll also review signals and systems material, but we're going to go deeper as we review it and talk about some trade-offs between, well, at least some issues about implementation complexity of the algorithms that we talk about. There'll also be some review later on in sampling and aliasing. We'll also go deeper, talk about some topics you haven't seen in sampling and aliasing, bandpass sampling being an example. So you have about 3 to maybe 3 weeks of review and going deeper in signals and systems. It's been a while. So I always like to ask this question: how many took signals and systems last semester? Okay, we got 3. How about 4? Okay, how about a year ago? Within the last year? So everyone goes up. Same, okay. Most folks. How about the last 2 years, between 1 and 2 years? How about more than 2 years ago? We don't know. 1 maybe. Okay, so the thing is, it's been a while, so it's in no one else in the overflow room. Okay, so, right. All right, so So it's been a while for some, and even in the context of, even to the last semester, there was a semester break. So we're going to review some of these things and go deeper as we go. I'm also going to spend some of the lecture periods to go over the homework solutions. So you'll come in, hand me the homework, I'll hand you the solution set as an exchange, and we'll go over it. So that's as fast as the feedback as I can give you as you walk in the door. And then we'll generally have the homeworks graded by the next Monday or the next lecture period to get that back to you graded.
Was JSK the lab book that we were
talking Yeah, so JSK is defined up here. JSK is the textbook, and the Welch, Wright, and Morrow is the lab manual. You can download all the lecture slides with one link or one click, and the course reader is also here. And this is a link to the video recordings in the multi-view format. Oh, so the pre-lab quiz is, no, there's no pre-lab quiz for the first lab. So the first pre-lab quiz will be due on Monday at 5 p.m. on January 27th, and it will be for lab number 2. Yes, every lab will have a pre-lab quiz. And the reason for that is, when I was a student, I didn't exactly prepare for lab very well. Like, I usually didn't come prepared, and I know that about myself. So as an instructor, I thought it'd be nice to have a very simple multiple choice test. You get 1 hour to do 10 multiple choice questions. Really, the intent is to get you to read the material ahead of time. And if you do come prepared, then you won't have to come back. You will finish all your lab work in the 3 hours of lab time. You won't have to come back at all, which is another bonus. That's it. Just the 3 hours will do. Okay. And some labs are more than 1 week, and we time them based on how long they do take to complete. So we have lab 1 is 1 week, lab 2 is 2 weeks, lab 3 is 4 weeks. So it just depends on the amount of time to complete. And honestly, the lab 3 on filters, actually we stretch it to 4 weeks because there's a midterm. So honestly, if you come in prepared and it goes reasonably well for you, you won't have any lab time during the week of the midterm. It's kind of a buffer week. And if you are having some issues, then you have some more time to work on it. Lab reports are due the week after your lab has ended. So the lab report for lab 1 is due week of January 27th. The lab report for lab 2 is due the week of February 10th, and so forth. Okay, so that means that the lab report for lab 3 is not due during the midterm week. That's the good news. The bad news is it's due the week after spring break. There's a little downside if you're a Monday lab person on that one, but otherwise, at least it gets the load off of the week of the midterm. Let's go back to slide 14. Okay. Okay, the other thing is, how's the weights work into letter grades? The average GPA for this class has been 3.1, right? So B is 3, B plus is 3.33, and A minus is 3.67, and so forth. So the average GPA has been 3.1 over the course of the class. And you can find this on MyEDU if you want to search for it. The data on MyEDU is accurate for this class. So it's going to break down some more of the homework. It's going to be 8 assignments, drop the lowest one. There'll be some theory, but mostly, especially after homework 0, it'll be mostly MATLAB work. So it'll be a little bit of analysis, a little bit of theory, a little bit of analysis, maybe mathematical analysis, and then MATLAB simulation. So you'll take existing MATLAB code that comes with the book. The book here is Johnson, Thesaurus, and Klein, and you'll modify the MATLAB code and test out some idea, some trade-off, and report and then talk about it in the write-up. So you would print and turn in your MATLAB code, turn in any plots you generate, and the write-up by hand. And you're welcome to type the whole thing. That's fine too. It happens. A little less common, but it happens. And so this is going to strengthen the theory and analysis. He'll translate the signal processing concepts, filtering and so forth, into MATLAB code. You'll see it work in MATLAB code, modify it slightly. And this is pretty common in industry. So if you go to work at a company, they've developed a lot of MATLAB simulations, most likely, if you work in this field, and you probably will go and modify existing code. It'd be unlikely that you develop a whole complex simulation from scratch at a company, either an internship or as a full-time employee. And in grad school, same story. If you join a research group, probably won't write something from scratch. You'll build on what other students have been doing in the research group. Pre-lab quizzes. Again, 10 multiple choice questions on the course Blackboard site. We'll give you 48 hours to do it, so we'll open the quiz Saturday at 5 p.m. and close it Monday at 5 p.m. So you take it any time during those 48 hours. If you have a problem, your roommate kicks out the gateway, power outage, whatever it is, send me email, I can reset your quiz. But I can look at how much you've done, I'll know how far along you are, and if you've answered probably 7 or more questions, I won't reset it. But I can tell if you were kicked out early, maybe you didn't answer any questions, I can see that on the Blackboard site and reset the quiz for you so you can retake it. You'll get a new set of questions, but at least you'll get a full shot at the 10 questions. Okay. The lab reports, you're going to work individually in labs 1 and 7 and teams of 2 in labs 2 through 6. So you will not need a lab partner until January 27th, or at least the week of January 27th. The attendance and participation in the lab section is required and will be graded. So it's important to have meaningful interactions with the TA, checking off results as they happen every 15, 20 minutes, something like that. Go ahead.
The lab reports that we do for our labs, are those going to be written like one report between?
Correct. There's one report per team. So it's a joint work, and we're going to assign the same grade to both. We're not going to be in any... We're not going to be in the position to say, you know, on the written part, you did more than the lab partner or vice versa, but what the TAs do know, because they're going to experience it, is how much each of you participated during the lab section. Okay. The lab reports are due the following week, that's right.
Just turn it in the lab?
Yeah, turn it in as you walk into lab the following week, that's right.
So you're saying that you submit hard copies, not soft copies?
Hard copies, that's correct, hard copies. Oh, I did forget one thing early on the last slide. I'm sorry, I did. Nope, not yet. It's coming. It's the last bullet on this slide. A couple semesters ago, a lot of things that happen in this class are because of student feedback, so please give me your feedback as well. For example, I used to have 4 homework assignments that were really long, and students said we would like to have them half as long. So I went with 8 homework assignments, half as long. So the same number of questions, just spread out over 8 weeks. For a couple semesters ago, students started asking me to include this on the slides. Now, right now, the graduate school deadlines were mainly in the fall. There are a couple that are right now, I suppose. But if you intend to ask me for a recommendation for graduate school, what I write in that recommendation is the rank in the class. So if you were number 2 out of 50, or number 1 out of 50, or 10 out of 50, whatever happens to be 20 out of 50, then I'll include that in the recommendation. I won't include the letter grade. The evaluation committee can get that from your transcript, but I will include the course rank. That's information they can't get from the transcript, and it's quite meaningful to the admissions committee. So just keep that in mind. So if you think about asking for a recommendation, then it's important to be, you know, the top part of the class, top probably 15 to 20% of the class would be ideal. Right, so you have 50 students, so top. You know, certainly the top 10% gives you 5, top 20% gives you 10. So being in the top 10 would be very helpful on the recommendation. Oh, so a couple of things here that almost finished with the course overview. A couple of things. So this was a student in fall 2010, and I do see him around. He's working in Austin. And he mentioned the following. The last day of lecture, he's a front row student. And he came to me and said, you know, the most important information in this class wasn't on the slides. Now, it's not to say that there's plenty of important stuff on the slides, but he said the most important stuff was not, got the wrong, sorry about that. So the most important stuff was not on the slides, which means that, now the good news is we got the videotape to go over for the lecture, and you're also present to take notes. So it's important to take notes either hard copy or on the PDF of the reader or right on the PowerPoint. So it's nice to be able to annotate notes as we go, which you can then use in homework and tests and so forth. The other thing that was interesting, that based on that comment, I also, in spring 2011, looked at the following: attendance in lecture, zeros on homework, and the final numeric grade. Now, I try to use a 10-point scale, so this would be an F, this would be a D+, this would be a C, 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 C. And I did notice a trend on lecture absences and zeros on homework. One exception, someone that turned in every homework and attended every lecture but still didn't do that well. But otherwise, it really is related to attendance and participation in homework. Probably not a surprise. Last thing to cover here on this slide is just to make sure you do your own work. So if you're a lab team, it's the two of you together on the lab report. And it's important to cite the sources for other work. I try to do that in my slides as best I can. So here and on homework, it's okay to discuss solutions with each other, but turn in your own, discuss the questions with each other, but make sure you turn in your own independent solution on the homework. And the same with the pre-lab quizzes. It's important that you take that as a quiz, not with someone helping you answer the questions. That one I can't monitor directly. I don't know. But anyway, so do your own independent work with the exception of lab reports 2 through 6. Now, this was an interesting thing. You can just read it for yourself. Interesting thing I had seen, I guess it was an IEEE publication. But so this can happen to anybody, not presenting your own work. So in 2006, William Swanson, CEO of Raytheon, was docked approximately $1 million in pay by the company after it was revealed he had plagiarized 16 of the 33 rules in his popular 2004 book, Swanson's Unwritten Rules of Management. So clearly, 16 of them had been written down by somebody else in his 33 rules. Now, this cost him $1 million. It's a pretty good chunk of change, but anyway, so just turn in your own independent work for homework and Lab 1-7 reports and pre-lab quizzes. Okay, so that's the end of the course overview, the course structure, I guess. And then we'll go on to back to some technical concepts. Before I move on, any questions on the grading, laboratory? Go ahead.
So those of us that are in the Monday section will be the last ones to.
Well, our intent is to start the Monday as the first lab section for that week. So because of the holiday on Monday, we're going to have to find another way to do that. Okay, so what I'm asking you to do, and if it's not possible, please let me know. We'll make other arrangements, is to attend one of the other 3 lab sections just next week. Okay. There's also some flexibility. You also need to find a lab partner, which may, do you have a partner already in mind? Okay. So for those that don't have partners, you may end up switching lab sections. And right now it's very fluid which lab section you may ultimately end up. Okay. So after class today, what I'll try to do is try to break out a little bit into lab sections and to see who's in your section, just so you have some idea. Because if we need to change sections, it needs to happen, I think tomorrow is the deadline. And we would do it manually in the undergraduate office. So that's the hope for the Monday. If you are registered for the Monday, so next week go to your officially registered lab section so you can find a lab partner for one, but also it helps us make sure that each lab is not overflowing. And then the Monday folks just spread out over Tuesday, Wednesday, and Friday lab sections. And it is a full lab section. I mean, it will go 2.5 hours next week. It is a full feature lab section next week. Any other questions? Pretty good. All right, so let's go on into communication systems. This is going to be our primary application during the semester. We'll do other ones. We'll do audio, we'll do image, do some video, do some biomedical instrumentation. But our primary application through the semester is communication system simulation and design and implementation. Now, the good news is it's a lot of signal processing. It's a lot of the things you've seen in the signals and systems prerequisite, but perhaps in a new light or a new application space. Because this application space is not required to be covered in signals and systems. So it's totally reasonable if this is a new application space. So for communication systems, we like to transmit a message or information source from a transmitter to a receiver. These are not going to be typically co-located. These are in different parts of the world or whatever, but close enough to communicate. And we like to transmit often voice, music, images, video, and data, and sometimes some combination of them. But one thing they have in common is that they have the power. If you look at the frequency content of these signals, they primarily have frequencies. The primary frequency content is near DC, which is zero frequency. And we call these baseband signals, as opposed to bandpass signals. I'll draw each example. We'll have examples in the next slide. But here's an example. I look at the frequency content. So this is the magnitude of the Fourier transform of the message signal. So an example of a baseband signal might be one that, and it should be symmetric and about zero. Okay, so that's an example of a baseband signal. The primary content in frequency domain is clustered around zero, and there may be no DC component. That also can happen, and that's okay. In this case, we do have a component at zero frequency, but we don't have to have a component at zero frequency. Now, this is baseband. Bandpass looks like what? How would you describe a bandpass signal? Yeah. Right, so the answer is it exists in a frequency range, not at 0, maybe 10 to 100, 10 to what, something kilohertz, 10 to 20, 10 to whatever. Yeah, so here's a bandpass waveform. Both are useful. So let's try bandpass. And where does bandpass fit in? It's often the transmitted waveform is bandpass. So the transmitter is going to do a fair amount of work, and in the end, not always, but more commonly than not, sends a bandpass waveform. And this is F in hertz. So a bandpass waveform might look like this. It's supposed to be symmetric about 0. So it's going to occupy a band of frequencies, but far away from the origin or zero frequency value. So the comment was this might be, for example, this might be, say, example, 10 kilohertz out to, say, 20 kilohertz, for example. Now, those are frequencies we can hear. If this were an audio signal or an acoustic signal, we could hear these frequencies. And then the same content here, so this would be minus 10 kilohertz and minus 20 kilohertz. So we're going to see even symmetric about, there'll be even symmetry about the zero frequency value. Now, there's a judgment call here because, as I mentioned, there are baseband signals that don't include any content at 0. So there is a judgment call as to what is bandpass, what is baseband in that case. So you could have a baseband signal, and this will happen to us quite a bit later in the semester, that I'll just draw a different type of spectrum. I guess it doesn't matter. I can do the same. So this could be a baseband signal. Because there isn't some break with 0. I'm still clustering the energy around 0. I just don't have any energy at 0. So this will be a judgment call, but I would call this baseband. Anyway, so that's our information source will be typically baseband, low frequency content. And you can kind of get a reason why this is important is actually in music. So in audible signals, or auditory signals, we generally, for normal hearing, do not hear frequencies below about 20 hertz. So even if there is content below 20 hertz, normal hearing would not hear it. So it's okay if it's zeroed out. So what you'll see in music signals and speech signals is that the DC value, which is the average value of the signal over time, is 0 or zeroed out. We don't hear it anyway, so why bother with it? Okay. In the transmitter, we have, in this very simple block diagram, which is a one-way communication system from a transmitter to receiver, we have two, break it down a little bit into the transmitter side, we have two basic blocks. We have baseband processing in the transmitter. At the very least, this would be some sort of filtering to limit the frequency content that we ultimately transmit in this signal S of t. The other things we can do here, and we'll do a lot more than that during the semester, we could, if the message signal were a bit stream, we could add redundancy in the bit stream so that the receiver can detect if there's been a mistake, a bit error in the receiver, if we put in some redundancy, which means at the very least repeat. So I take every bit that comes in, we may just repeat it, or we can do something more interesting like a parity code or parity check. So what a parity check does is, let's say I have a 7-bit number. The parity bit would tell me how many ones, for example. Is it I have an even number of 1 bits or an odd number of 1 bits? 1, 2, 3, 4. So this would be now, this is in total 8 bits. And the parity bit could be either odd or even parity, but just as an example, if I have an even number of 1 bits, I can call this 0. And in the receiver, if I look at this 8-bit value, if 1 bit has been flipped, the parity will be wrong. And I can detect that there's been a flip of 1 bit. So what if the parity bit flips? So let's say the parity bit flips. Can I detect that as a mistake? Yeah, because if these bits are done correctly, then the parity bit will be incorrect. Now the problem is, with the parity code, what if I have 3-bit flips? I may not check, so 3-bit flips I'll be able to flag, but 2-bit flips, right? So if I flip this to 0, if I do, let's see, if I flip this to 0 and flip this to 0, parity hasn't changed. Right, so this is parity codes are nice, but they really, this particular type of parity only I have 1 bit of redundancy, and so I can check if there's 1-bit flip, but I'm not going to be able to catch 2. I'd have to add more redundant bits to be able to catch 2 flips, which I can also do in practice. Okay, so we'll come back to this a bit later, although we won't spend a lot of time on the coding aspect of this. This is a type of thing called channel coding. I'm not going to speak much about that, and it will come up a couple times that we're not going to dwell on it, but just to make you aware of it. So it is possible, with the right choice of redundancy, for the receiver to flag if there's been a bit flip, and in some cases, the receiver can correct for that bit flip, which is great because then I don't have to retransmit the data. All right, so that's the baseband processing in the transmitter. And in lab, we're going to do all of this baseband processing in discrete time, digital amplitude on the embedded processor, on the digital signal processor in lab. And homework, we'll do this primarily in discrete time and digital in MATLAB. And we'll use floating point in both cases. Okay, so right here I'm showing you continuous time analog from start to finish, but as we go a little bit farther into this material, we're going to do the work in the baseband domain, or for the baseband signal, in discrete time. Okay, so let's talk a bit more about the rest of the transmitter. So we've got carrier circuits in the transmitter. The job of the carrier circuit is to take the baseband signal that's been output from the baseband processing block and put it up into frequencies that will typically transmit better, has more reliability to get to the receiver. And the actual band of frequencies that the carrier circuits will move the baseband signal to, its output, which is the up-converted signal, depends on whatever the application happens to be. Okay, so let's talk about some examples of that. So the first example, let's see, put sort of AM radio. Okay, so for AM radio, I'm going to ask you what's the, so for AM radio we have a couple things to worry about here in the plot, is I need to know the bandwidth of the baseband signal. That's omega 1. Here I'm radians per second, I suppose, but I can switch back to hertz. So for AM radio, the bandwidth, the audible bandwidth, is pretty low. Okay, it's 5 kilohertz. We're missing a lot of the frequencies we can hear. One of the reasons AM radio isn't the best choice for high-quality music. It's fine for speech, talk radio, whatever. And the next thing is, what's the carrier frequency? It's in the megahertz range. That's right, so the middle of the band is 1 megahertz. Where's the band? I always have to look this up. So where does the band begin? Yeah, it's pretty close. Yeah, I'm going to go with 550, but please check this. So let me put a question mark. And this is important, and everything I say you should be critically evaluating, and everything you read you should be critically evaluating. But at least, honestly, I'm going to tell you, I didn't look it up. I know it's about 550. And what's the other end of the, and this is in the US, I also have to say, this is US. What's your upper end of the AM radio? You're close to 2 megahertz. Okay, I think 1710 is what I'm going to go with. And again, I'm going to put question marks on that one. And the midpoint's a megahertz, right? So the roughly is a megahertz. And this next thing is this. This is the baseband bandwidth. So this is baseband. There's also a bandwidth for transmission, right? The transmission bandwidth is how wide for AM radio. If this is 5 kilohertz, this is 2 pi times 5 kilohertz. That edge is 2 pi times 5 kilohertz. So what happens in upconversion? Well, in principle, we take the baseband signal, we shift it to the right by the carrier frequency, and we shift it to the left by the carrier frequency, and we scale by a half. Now, one way we can do this is multiply by a cosine. This is the modulation property. So one way, it's not the only way, one way to affect this in the block for the carrier circuits is to use multiplication by a cosine, 2 pi f naught t, right? Where omega naught is simply 2 pi f naught. Oops. Go ahead.
When would you use something different than the single cosine?
There are a couple other ways that you can do the upconversion. One is through sampling. We'll talk about this in lecture 4. And there are some nonlinear ways to do this that that also can be employed. You can do squaring devices. There are different ways to get that frequency content from baseband to a higher band. So you can do a squaring device and a bandpass filter is one way to double. So there's different ways that you can pull this off. This is the starting point, which is multiplying by cosine. This is the one. This is a Fourier transform property. So we would take the output of the baseband processing and produce S of t. This is the mathematical view. There's a lot of design work to make this happen. Okay, so then back to this. So what's the transmission bandwidth? Okay, so how wide is this? 10 kilohertz. So how wide is this? 10 kilohertz. All right, so it's just that this baseband spectrum gets shifted to the right by the carrier frequency, scaled by half, shifted to the left by the carrier frequency and scaled by half. So the transmission bandwidth and so your channel spacings in AM radio in the US are separated by 10 kilohertz. So you have 550, 560, 570, etc. So if you look at a radio station, they're not going to say tune in to 553. They're going to say tune in to 550 or, I don't know, does anyone still listen to The Zone for UT Sports every now and then? I don't know. Okay, so that's at what frequency? 1300 kilohertz or 1.3 megahertz. Not 1303 or 1298. It's at 13 kilohertz, 1300 kilohertz. All right, now the carrier circuits in a mathematical model would have this multiplication by a cosine, and then we follow it with a bandpass filter just to enforce the transmission band that we're supposed to use. And one of the reasons, so why do we need to do that? We don't take up other channels. So there are, again, the circuit design is going to have some noise and some nonlinearities in it, most likely. Some effects that are not completely predicted by a linear time invariant analysis, which is what this sort of is, or linear system analysis. This is time varying. So in the implementation, you follow it with a bandpass filter, and that bandpass filter would pass the transmission band and try to attenuate frequencies outside that transmission band. So we don't interfere with other AM stations. So AM radio is based on this mathematical model of multiplying by a time-varying cosine at fixed frequency f naught, and that fixed frequency f naught is the radio station frequency. This is the mathematical model, not the circuit implementation. Okay, that's the transmitter side. On the receiver side, so let's first talk about the channel, which is our route to the receiver. So we want to transmit this S of t signal, and that transmission could be over the air like AM radio. It could be through a wire. It could be through lots of different media. It could be underwater. It could be through the water. Lots of different ways to transmit S of t. Whether it's wired or wireless as a transmission medium, the transmission S of t will propagate, and a propagating signal will spread, and over time will spread out in the time domain, and it will typically lose energy. So it will attenuate in amplitude. And there's some ways that we can improve reception before the signal finally hits the receiver, which is R of t. So one thing we can do is called boosting, which is to put some additional, you might say relays is another way to think about this. Between transmitter and receiver, we might put a relay in the channel just to rebroadcast or retransmit the signal. And what I can do very simply is to, at the very least, I can apply a bandpass filter to enforce the transmission band, and then I can boost the amplitude. So here's just a gain, some constant A. All right, so at the very least, I can filter and amplify. Go ahead.
Wouldn't the amplifier introduce more noise?
That is correct. So you want to design this amplifier so that over the transmission band you don't get any bizarre effects. So you could decide to switch the order,
Yeah.
which would make a little more sense, because otherwise I'd have to put another bandpass filter here. So we could do it instead. Put the gain and follow that by a bandpass filter. Now, what happens in cellular systems for base stations and there are, in today's deployments, relays, and they have different names. And the idea of the relay is to get a better signal to you, or in some cases, get a signal to you. Okay, so you can think about a base station mounted on top of a building in an urban setting, and there are some places around the base station that it can't get a good signal to. And so what we do in deployments is put what's called pico cells, which are going to be on lampposts and so forth, to then serve as where you get your signal. And if that doesn't work, then you can get something for your house, which is a small cell, used to be called a femtocell, which is something a little bigger than a hand that would serve you the signal. So the femtocell would communicate back to the base station, or the pico would communicate back to the base station. So they act as a relay. It's more sophisticated than obviously gain and filter. It's a lot more involved than that. But your signal may not come from a tower-mounted macro base station. They come instead from a pico at the street level or a femto from your house. For the very reason of signal spreading and attenuating over distance. Okay. At the receiver, we've got a lot of work to do. The receiver, at the very least, has to undo the steps in the transmitter. So the carrier circuit block would go from bandpass receive signal R of T and take this down to baseband. And then it could be baseband plus other. And then the baseband processing would then extract the baseband part. And so the ultimate goal for the end of at the receiver output is to give a estimate of the transmitted signal that has the highest signal quality possible. So again, our starting point would be signal to noise ratio. We'd like to have the highest signal to noise ratio possible. Okay, so this is the, we're going to see this kind of block diagram during the semester, all the way almost to the end. So this is a pretty common one, but a very high level treatment here. And we're going to dive into these blocks as we go through the semester. Questions on? So it's a good time to review some basic Fourier transforms, and we just use the modulation property to convert from baseband to bandpass transmission. Now, in practice, we're going to have more commonly a two-way communication. So at the receiver side, there'll be a transmitter here that also will send signals back to a receiver on this side. So more commonly, we'll implement in practice a chip or a board that does both transmission and reception. And then on the other side, where you're connected to, there'll be a transmitter and receiver there as well. And we combine that, and it's called a transceiver, just for easier pronunciation. But this class, we're mostly going to do the one-way just because that's important to understand as a building block for the two-way system. Okay, so in the minute that remains, this is the last slide for today. This is the laboratories that we'll do, and they all relate. The first labs are very basic building blocks of signal processing systems, generating sinusoids, filtering, and generating periodic structured noise. These are useful in all kinds of systems: audio, speech, video, image, biomedical instrumentation. We'll then do 2 labs specific to communication systems, digital communication systems, and then the lab 7 will be digital audio effects, guitar effects. Now, I point out here on the right-hand side that these building blocks in labs 2 through 4, and lab 1 is just a general introduction, so it's also useful generically, is how does that translate into communication system algorithms, operations, and subsystems. That's on the right-hand side here. So what will happen is what we do in labs 1 through 4, we will then turn around and build upon in labs 5 and 6. So in the end, lab 6 will be a system design that uses everything from labs 1 through 5. Lab 7 in digital and the guitar effects will use labs 1 through 3 to build delay and echo effects for audio. So again, very generic building blocks, labs 1 through 4, and then applications, labs 5 through 7. And the applications are after spring break. Any questions before we end the recording? All right, well, have a great Wednesday. We'll see you on Friday.